Suppose a local bank advertises that it compounds interest continuously and that it'll double your money in 12 years. What is its annual interest rate? Well, we are told that it'll double your money in 12 years. So that is the doubling time. So here our doubling time, capital T, is 12. Well, we know that from our notes, we have that K, the rate, the growth rate, is equal to natural log of 2 divided by T, the doubling time. So to find the annual interest rate, we plug in 12 for T. So we have natural log of 2 divided by 12. And then when we approximate that, we get 0.0578, which is 5.78%. So the annual interest rate in this case is 5.78%, rounded to 2 decimal places. In 2009, U.S. per capita personal income I was $48,040. In 2012, it was $52,430. Assume that the growth of the U.S. per capita personal income follows an exponential model. Letting t equal 0 be 2009, find the exponential growth function I of t. So we're looking to find the exponential model. We're going to use I of t, and that's going to be equal to I sub 0, our initial income, times e to the kt, where k is the growth rate. Here we're letting t sub 0 be 2009, so our starting time is 2009. Well, in 2009, we know what the personal income was. It was $48,040. So that is our initial income. I sub 0 is equal to 48,040. So let's go ahead and plug that into our equation. So now what we need to find is K, the growth rate. And we're not given the growth rate. However, we are told that in 2012, the income was $52,430. So we can use that piece of information to figure out what K is. So 2012 would be 3 years from our initial time, since we're starting in 2009. So 3 years later, when t is equal to 3, we get a function value, or an income value of $52,430. So we can use this, plug 3 in for t, and set our function equal to 52,430. So that's going to look like 52,430 is what we get as a function value when we take and plug in 3 for t. Alright, so now what we can do is solve for k. To solve for k, notice k is in our exponent, so we're solving an exponential equation here. So first of all, we need to get rid of this constant that's out front of our e. So I'm going to divide both sides by 48,400. So when I divide both sides by 48,040, I have 52,430 divided by 48,040 equal to e to the 3k. Rather than working with this large looking fraction here, I'm going to get a decimal approximation for this. So if we round to, let's say, 4 decimal places, we have 1.0914 is equal to e to the 3k. Now, in order to get our variable out of the exponent, we're going to have to take the natural log of both sides of this equation. So I'm going to kind of move over here and take the natural log of both sides. So I have natural log of 1.0914 is equal to the natural log of e to the 3k. Now, one of the properties of logarithms tells us that we can bring the exponent out in front. So when we do that, we're going to have a natural log of 1.0914 equal to 3k times the natural log of e. Well, we know natural log of e is just 1, so that's going to go away. Now I need to solve for k. So divide both sides by 3. So I get that k then is equal to the natural log of 1.0914 divided by 3. Alright, so now let me get a decimal approximation for k by plugging that in the calculator. And since I haven't really specified what we should round to in this case, let's round to 3 decimal places. So we get a 0.29 here when we approximate k to 3 decimal places. So now we have our k value, our growth rate. So now going back to our original equation here that we were trying to set up, that was what we were missing. We had our initial population and now we have our k. So now we can go back to this equation here and plug that in and we will have our exponential growth function. So we have I sub t is equal to 48,040 times e to the 0.029 times t. Alright, and there is our exponential growth function that we were trying to come up with. So now in part B, we want to predict what U.S. per capita income will be in 2020. Well, our initial time t equals 0 is 2009. So if we're talking 2020 minus 2009, that is going to be 11 years later. So when t equals 11, we want to know what the income is. So we're going to plug 11 into our function. So we have 48,040 times e to the 0.029 times 11. Now when we put this in our calculator, what we get is approximately $66,091, rounded to the nearest dollar, for the per capita income in 2020. Now I should point out that back in part A, when we were calculating our k value, we rounded this off to 3 decimal places. Now if we would have given a better approximation and left more decimal places here, that would affect our answer in part B. Our answer would be slightly different depending on how many decimal places we wrote our k value out to. For part C, in what year will U.S. per capita income be double that of 2009? So here we want to find the doubling time. So t is equal to natural log of 2 divided by k. So to find doubling time t, we take natural log of 2 and divide it by our growth rate k. So we have natural log of 2 divided by, and we found the growth rate k to be 0.029. So now approximating that using our calculator, we get approximately 23.9 years. So now we want to know what year. So we need to add 23.9 to 2009. So 2009 plus 23.9 gives us 2032.9. So technically we would be in the year 2032, but we'd be towards the end of that year. So we could say in year 2032, the U.S. per capita income would be double that of 2009. But we would be getting pretty close to the year 2033.